So today you're learning the last section in chapter 6, and it's on geometric probability. Your favorite subject, right? So 10-6, geometric probability. So we have some postulates. Postulate 10-3. It's called your length probability. Postulate. And it says, if a point on AB, line segment AB, is chosen at random, and C, that would be point C, is between A and B, points A and B, then the probability that the point is on line segment AC is. And I'm going to give you a ratio. But first, let's draw a picture. So it says if a point on line segment AB is chosen at random and C is between A and B. So that means that A and B must be on the ends and C is somewhere in the middle. It doesn't necessarily mean it's directly in the middle. C could be here, C could be here, C could be directly in the middle, or it could be whatever. So, I don't know, I just tend to put C wherever. Bless you. Then it goes on to say, then the probability that the point is on AC, so from here to here. General probability, isn't it favorable over total possibilities? What you want to happen divided by all the possibilities that could happen. So if this is what I want to happen, we're going to take the length of segment AC and divide it by the length of segment AB, because those are all the possibilities. Then the second postulate that we're going to work with today is this. So postulate 10-4. Thanks, Chase. Is your area probability. Nice of you to join us, ladies. Is your area probability postulate. And it says, if a point in region A is chosen at random, it'd be nice if we could all get here on time. This is the second interruption. Then the probability that the line is in sorry, I got distracted. Then the probability that that point is in region B, which is in the interior of region A, is. So we're going to draw a picture and come up with a ratio. So there's a couple of different possibilities you could have, so I'm going to draw a couple of different pictures. You have one picture of a circle in a circle. And so this would be region A and this would be region B. So they want to know that if a point in region A is chosen at random, so anywhere in this outer ring, then the probability that the point is in region B, region A is the entire circle including region B. And they want to know what's the probability that I would land in region B. I could also ask you region A also, but the way they're describing the postulant, they're talking about landing in this region, which this looks like a dartboard, doesn't it? With a few less rings, right? So the probability of landing here is harder than actually landing out here. And it doesn't matter that it's directly in the center. I could have put this circle, same size circle, anywhere in here and the probability would still remain the same. It doesn't matter where it's placed in that larger region. It's the matter of what is its size versus the larger region size. Or I could have a square I could have any shape polygon. And then let's just put a circle in there. So this would be region A, and this would be region B. I could come up with an infinite number of possibilities, but here's two different ones. So what do you think is our favorable outcome? If I want to know the probability of landing in region B. Area probability postulate. What do you think I might want to find? The area of region B. So you would take your area of region B, which is the smaller one, the one that's in the interior of the larger one, and divide it by the total possibility, which would be the area of the whole larger region, and in both of these cases would be the area of region A. So we're going to look at a couple of examples. And you're going to find some of these questions tonight also challenging or difficult. Just depends on how comfortable you are with probability and whether you understand what they're asking for. So example 1. Somewhat lengthy. Joanna designed a new dart game. A dart in section A earns 10 points. A dart in section B earns 5 points. A dart in section C earns 2 points. find the probability of earning each score. Round to the nearest hundredth. Oops, that's just a 1. So here's what her dartboard looks like. Oh, by the way. So this is area A, B, and C. And I'm not saying that I just drew it true to form, but we're going to go with that. And then you need to know some additional information. So additional information is given to you, and it is that the radius of circle A is equal to 2 inches, and the radius of circle B is equal to 5 inches, and then the radius of circle C is equal to 10 inches. So we want to know the probability of earning each score, so an A, a B, and a C. So we're just going to start with the probability of score A. Bless you. And so wouldn't I want the area of A over the area of what? What's the overall biggest area? C. Now the area of C is not the ring per se. We're talking about C plus B plus A. We're talking about the whole, all 3 circles together for the area of C. When we find the probability of C, we're of course going to want to find the ring. But for right now, we're going to find the area of A. And so, this is the area that I'm finding right now. So these are all circles. What's the area formula for a circle? Pi r squared. So, the radius of A is 2. So don't I just do 2 squared, which is what? 4. And then can't I just tack on pi? So the area of A is 4 pi. And yes, it's inches squared, but when I divide it by the area of C, won't that be inches squared, and won't they cancel out? I am going to ignore inches for right now. So then let's find the area of C, meaning CB plus A. The whole radius of C from the center here all the way out to C is 10 inches. So what's 10 squared? 100. Tack pi onto that. So don't the pi's cancel, and what else cancels? 4 goes into 100 how many times? 25 times. Now technically, the exact answer is 1/25th, but the directions did say, and I'm, by the way, perfectly happy with that fraction. So the directions did say round to the nearest tenth, so all you're going to do is take 1, divide it by 25, and I get 0.04. Or, I'm sorry, round to the nearest hundredth. So that's exactly equal to 0.04. If I wanted to know what percent probability, what percent would that be? Move the decimal 2 places to the right, you would have 4%, right? But that's really the answer that they were looking for. In my world, 1/25th, 0.04, or 4% are all acceptable answers. All right, so then let's look at section B. So the probability of section B is equal to, now B is a little bit trickier, because B is just a ring, right? B is this ring right here. So I can't just take the area of B by taking 5 squared and saying it's 25 pi. I have to take the whole area of B and take out the area of A, don't I? So the area of B minus the area of A, all divided by the area of C, which we've already configured the area of C. So the area of B would be the 5 squared, which is 25 pi, minus, we already know the area of A, because we figured that out before, 4 pi, all divided by, we already found the area of C, which is 100 pi. So what's 25 minus 4? So we get 21 pi all over 100 pi. The pi's cancel, right? The only numbers that go into 21 are 3 and 7. Does 3 or 7 divide into 100? No. So the exact fraction answer would be 21 100ths. If I divide that, what decimal am I going to get? 0.21, which is the answer they're looking for, or isn't that 21%? I didn't have to use a calculator because aren't percents based on 100? And if I'm dividing by 100, I move the decimal 2 places to the left. But if you're happy, you can use a calculator for that. All right, then the last thing that they're looking for is the probability of landing in ring C. Ring C's area is not 100 pi. That's a whole circle C. So for the probability, I'm going to move this, well, maybe I don't have to move it up. Probability of C would be area of C minus what? What am I going to take out to get that ring C? If I take out circle B, doesn't circle A come with it? Right? So all I have to do is take away area B and divide by area C. So area C we already calculated is 100 pi minus area B we calculated was 25 pi, all divided by 100 pi. The 100 pi's cannot cancel because there's a subtraction sign here. So we get 100 minus 25, 75 pi, all divided by 100 pi. What can reduce? The pi's. And what goes into 75 and 100? 25. So 25 goes in here 3 times and in here 4 times. Bless you. It's the cutest sneeze ever. And your oops, I don't know where the 5 came from. Your fraction answer is 3/4. What decimal is 3/4? So 0.75, that's what they're looking for, or isn't that 75%? So according to their, my picture probably isn't exactly accurate, but according to their point totals, does it make sense that she is giving section A 10 points because it has the smallest probability of being hit, and then section C has 2 points because it has the highest probability of being hit? Okay, then one other thing, do you remember on your Ames review that there was a question regarding the area of what's called a sector in a circle? It looks like the pie area of a piece of pie in a pie. If I took a slice of pie, it's that weird triangle-y shape, but it has a curve to it, right? Because it's coming out of a circle. Well, we can find the area of that slice of pie. So, area of a sector, and this is the last thing besides volume and surface area that's on your Ames reference sheet. So area of a sector of a circle. Interruption number 3. Jeepers, somebody's leaving already? It's only first period. Colt, you can go in just a minute. Finish my lecture. All right, so the formula is N And I'll tell you what n is in a minute. N divided by 360 times pi r squared. What do you think n is? What? Well, pi r squared is the whole area of the circle, right? Where does 360 come from in a circle? The degrees of a circle. So think of a slice of pie in a circle. What does the sides of the slice of that pie represent in the circle? Radiuses. And what do those radiuses create? What kind of angle? Central angle. So n is equal to your central angle. It's the measure of your central angle. All right, so example 2, last example. And then we'll do a couple things on your study guide. Scott is planning a circular flower bed circular flower garden with a radius of 2 meters. He plans to plant tulips, not 4 lips, but tulips. That was a joke. He really is. You're not even paying attention to me. He plans to plant tulips in the sectors marked with a T. And daffodils in the sectors marked with a D. What is the area that will be planted with tulips? And here's a picture. All right, so I have put in here that from here to here is 180 degrees because this is a diameter, and that this is 60, 30, 60, and 30. And that adds up to 180. And then I also wrote in here that the radius is 2 meters. So are all the tulip sections the same? degrees. What's the degree here? Y. It is 60, but why? What are these to each other? Vertical angles. So what's this right here? 30. And then this would also be 60. So do all the tulips have the same central angle? Yes. So how many of them are there? 4 of them, right? So I need to find the area of this, and this. Because they're asking, what is the area that will be planted with tulips? So area of tulips is equal to, the measure of my central angle is 60 degrees, so I'm plugging that in, divided by 360 times pi, and then I have to put my radius in and square it, which is 2 meters. Is there anything else I have to do? I could do all this and then at the end do what? Multiply by 4, or I could multiply by 4 right now. It's your choice. I think I'll wait till the end. So then I end up with, the zeros cancel, the 6 cancels into 36 6 times. So I have 1 over 6 times 2 meters times 2 meters is 4 meters squared over 1 times pi over 1. Doesn't a 2 go into the 6 and 4? And so my exact area, because I always liked exact, is 2 pi over 3 meters squared. That's my exact area. But that's only of one sector. So I want the area of 4 sectors. So 4 times the area of a tulip is equal to 4 over 1 times 2 pi over 3 meters squared. What does that equal? Nothing cancels. What does that equal? 8 pi over 3 meters squared. Now, if your book gives you a decimal answer, then you're going to take 8 times 3.14 divided by 3 and compare it to the answer. But I want the exact. Yeah. Well, let me give you some stuff first. All right. So then here is your. I'm going to take this. Oh, here's a study guide. We'll look at just a couple of questions on here. Have you taken no notes? Really? Because I don't see any notes on your paper. You should take exactly every note that I write down. And you haven't written down one word. Cell phones are put away, we can see them out. Okay, so a lot of what I said is restated up here, and I go over an area problem here. So I really wanted to look at this segment right here. So it says, find the probability that a point chosen at random on AH, from here to here, is also a part of each of the following segments. I assume the 12 shortest segments are all congruent. In other words, the distance from 0 to 1, 1 to 2, 2 to 3, and so forth, that they're all the same distance apart. So, AB. How far is it from A to D? 5. So wouldn't you do 5 divided by the entire distance is what? So the probability that a point would land on AB is just by 12. What about A to E? 7, so those are easy to count, right? Over 12, so 7 12ths, that doesn't reduce. What about DE? 2. Now be careful on your homework because they might not count by 1s here. If they count by 2s, you have to count by 2s. So do be careful because oftentimes they're going to partition this out differently, so don't fall into that trap. So you do have 2 over 12, doesn't that reduce to 1/6? And then what's CG? 7 over 12. So AE and CG have equal probabilities, correct? And they did not say round to the nearest hundredth, so I would not be cracking out the calculator and giving the decimal answer. All right, then let's look at 5 and 6. Your knowledge of area yesterday is going to come into play here. It says, find the probability that a point chosen at random in each figure lies in the shaded region. Round your answers to the nearest hundredth. I am going to have to make some assumptions on question number 5. What's the assumption that I'm going to have to make? That what? That I have right angles. What am I going to have to assume about this figure? What shape is it? I'm going to have to assume it's a rhombus. Now if you look at everything, this is an 8x6, 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 8x6 triangle, right? Shouldn't all of these hypotenuse be the same? So the assumption that I'm making that it's a rhombus is accurate as long as I have 4 right angles, correct? So what's the area for a rhombus? Yeah, well, no. Area for a rhombus is 1/2 what? D1 times D2. So that means I need to know the diagonals. What's the length of this diagonal here? Bring it all the way out to the side here. What's the length? 12, right? So 1/2 times, and it's 12 units. And then the length of this longer diagonal is what? Yeah, from here to here is 16 units. So that actually wasn't as difficult as we thought, but you do have to know what your area formula is in order to answer it. So then, handy dandy calculator. 12 times 16 is equal to 192, then divided by 2. So 96, no need to round to the nearest hundredth, but technically, what was it, 96? 96.00 units squared. They want it to the nearest hundredth, and that's technically out to the nearest hundredth. But if you wrote 96 units squared, I probably would have marked you wrong. Then here, and so we're not done yet, it says find the probability that a point chosen at random in each figure lies in the shaded region. So I just found the area of the shaded region. Don't I have to know the area of the entire region? So this is the rhombus. The area of the rectangle is equal to length times width. So my length is 16 units and my width is 12 units. And we already found 16 times 12 was 192. So that's my area of my rectangle. Rectangle is the whole thing. So to find the probability, put that up here. The probability of landing in the shaded region is favorable, so I'm going to put the 96 over the 192 because that's the entire whole region. Well, that was a quick visit. So 96 divided by 192 is equal to 50%, right? Or, but they want it rounded to the nearest hundredth. So would that equal 0.50? And then for this one, we'll do one more. Do you want to do 6 or 7? 7? Okay. So remember, on this one, you'll take the area of the outside, which is 12 by 12, subtract the area of the inside, which you know the diameter is 12, so the radius is 6, right? And then you'd put that difference in the numerator all over the 12 by 12, and that would be your probability. So for this one, we have to find the area of this sector and subtract it from the entire area. This sector, they told us, is 120. So the area of the sector is equal to 120 over 360 times pi r squared. I'm going to put that over 1. The radius is the 9, right? So my zeros cancel, my 12 cancels into 36 3 times. I end up with 81 pi over 3. And doesn't this 3 cancel into the 81 how many times? 27 times. So the area of the sector, the exact area, is 27 pi units squared, whatever it might be. So I need to find the area of the shaded region though. So the area of the shaded region would be the entire area of the circle, which wouldn't that be pi r squared? So isn't the entire area of the circle 81 pi? Minus the 27 pi. So what does that equal? 81 pi minus 27 pi. What's 81 minus 27? You do the math. I already know how to do it. 54. So the area of the shaded region is 54 units squared. Now how do I find the probability? What do I do for probability? What's your favorable? Isn't this your favorable? The 54? So the 54 pi is divided by what's the area of the entire region? The whole circle. What's the whole circle area? 81 pi. And the pi's cancel. And then you're going to get out your handy dandy calculator. And 54 divided by 81. Round that to the nearest hundredth. What's it going to be? 0.67. So it is equal to 0.67. So you're going to use some of your knowledge from yesterday in today.